This was the center of a circle. Please do notice the best diagram is what again I am putting in front of you. And the charge particle is here. Given velocity v, there's a mag field into the plane. It is having a width x, then it will emerge through the field with a tangential velocity v. This is the center. Oh, now look at the part of a circle. There's a part of a circle, no? What we have shown, only this one. What we think it's some parabola, no, part of a circle. So whenever a charge particle enters a magnetic field, so what is that? Like a path of a charge particle in a magnetic field, it will be a part of a circle. Finish over. So what is that arc OP? It's a part of a circle. Where C the center of curvature. So this C, it should be here only. It depends upon where these two lines will intersect. The radius vectors where they intersect, there's a center of curvature. Here in the diagram, I just picked up here. If the magnetic field strength can be like this, hope some common sense should be there. It should not be always at the vertex. Even this field strength I can extend like this till here, no? Okay, so therefore, when a charge particle enters a magnetic field, the path of a charge particle will be a part of a circle. There's a primary condition. When a magnetic field, when a charge particle, when a charged particle enters the magnetic field, the path will be a part of a circle. If it is projected inside a magnetic field, then it will be a complete circle. I think this is the trick. Finish over. You have some around 200 numericals are there. Not 1, 2. A student must have some small basic idea. So what type of charge particle we have projected? We have projected a positive charge particle. Even negative charge particle, the discussion will remain same. Hope everyone is able to get the methodology here, involve the methodology involved. Next, after this, will vary the width of the field. The first case, I'll discuss all the situations one by one. This is very important. Please do think, you know, mass circles. I think you're going to learn like anything. Applies 1% here. That is more than enough. 1% I'm requesting. 1% of circles, what you learn. Circles, triangle, more than enough here. Now, first x equal to r by 2. What will be the deviation? We'll make it some pink line. Thin line will make it the one which is a part of circle. Now I have to take the strips. I will try to get the problem. Let me explain through the diagram. X equal to r by 2. I think look at the strip. It is now the charge particle here will put a charge particle. It is projected. It will emerge here. What is this? This is what x equal to r by 2. May not appear. Okay, this will be the radius of circular path. First case it is Okay, remaining things I'll go for a rough diagram because it'll take more time. So this will be our radius. Yeah, we ended up. So this will be the center. It need not be always at this particular point. I hope everyone able to understand here, common sense. Sir, the center of circle should be always at the vertex of this strip of magnetic field. Need not. Even I can extend this particular thing till here, no? It's a strip here. So this will be theta. And what is the deviation? I'm asking you. So what we know the formula, sine theta equal to x by r. What is x equal to r by 2? First condition, x equal to r by 2. So this is r. So therefore theta equal to pi by 6. Then what is the time it will spend? What is the time it will spend? We know omega equal to theta by t. Omega is constant, which is equal to b alpha or bq by m. Theta is how much? Pi by 6. So time spent is equal to pi m by 6 bq. The charged particle will take this much of time. It will spend this much of time only. Then what is the x coordinate? X equal to already you know x equal to r by 2. Y coordinate we can calculate. What is the deviation? Deviation is pi by 6. Theta is called as a deviation. We have one more, deflection. Anybody? Deflection, can you define? Deviation is how much? Pi by 6, I said. I am asking now the deflection. Let me have water. Deflection, try to think. I find the deflection of the charged particle when x equal to r by 2. Let me have water, where r is equal to mv by qb. Anybody deflection? I want, I'm testing your language. Deviation, deflection. I got one response. Let me see. Displacement covered by the particle from initial moment to till it exits the field. Deflection, deflection. Ananta Krishnan, think once again. Change in y coordinate. Okay, yeah, Srivastava, fine. I think there's a lot of problem with our language. Am I right? Are we really very good with our language? It's a million word question mark. The technical words, I'm telling this one, language is not something like writing poems and prose. In science and technology, the technical words having a lot of meaning here. The knowledge depends also on the language. Many say that okay, science doesn't need language. Deviation, deflection. What do you mean by deflection? Why is it deflection? It get deflected. Deviation is different. Deflection is different. This y will become deflection. We know already we have discussed this. Cos theta, cos, this will be √3/2. So this is deflection. Hope everyone is able to, sir, why it is? Because there's a difference there. Deviation is an angular measurement. Deflection is something vertical deflection. Vertical, how much it gets deflected. The particle was earlier moving horizontally. Now it is moving at an angle. So it got deflected, no? It get deflected. Deviation is for that angular change. Deflection is for vertical displacement. Okay, yeah, be careful. These are the, I think you look at the SEO, you do have this question. So maximum 90% of students, they'll ask me, sir, deflection means what? Like, I don't know. We have deep root problems in our language also. Technical language is something very essential. Whenever you get a free time, why don't you just brush up all these words? Now we'll go for x equal to r/√2. Next condition, let me make x equal to r/√2. I think the diagram will remain same almost. We'll copy this. Cannot fit here. Yeah. Next will second situation, x equal to r/√2. X equal to r/√2. So the particle will enter at t equal to 0 after some time t limit. Again, we have to find out all the quantities. What is the deviation given by the formula? Sine theta. Let me define all those things here. Sine theta is equal to, I think I have to dump here only. Sine theta equal to, we know x by r. X equal to r/√2. This is r 1/2. So the deviation will become 45 degrees or pi/4. Then what is the x coordinate? X is the thing what we have defined it. Agreed. Then the deflection will change. Time spent, omega equal to theta/t. Theta is what? 45 degrees, pi/4 t. And we know omega equal to bq/m. So time spent will be pi m/4 bq. Or you can also find out arc length. What is the time spent? Arc length by speed. You'll get the same thing. Time equal to, we can also write arc length by speed. Okay, no? As it is moving with a constant speed, the work done by magnetic field is 0. The conditions will be same. Now, where it's going to live, it's not going to live at same point. The point P will get shifted up because the y value will change. You see, y equal to how much? R into 1 minus cos theta. R equal to mv/qb. This will be 1 minus 1/√2. Will it leave the magnetic field at same point like earlier, or will it be a different? No, it will be a different point. Maybe the diagram appears similar because they just copied. It is going to now get deflected by some other distance. Earlier it was 1 minus √3/2. Now 1 minus 1/√2. So now I want to change the direction of charged particle. Tell me, what shall I do? Just vary the width of magnetic field. By varying the width of magnetic field, what we can do? We can control the deviation. This is very important because I want to control the path of a charged particle. Whose help I should take? Just bring the magnetic field. Sir, already electrostatic field is there. I will take help of it. Electrostatic force, it will do work. I don't want change in kinetic energy of charged particle. I just want only change in direction. So whose help I should take? So let me take better help of the magnetic field only, because the work done by magnetic field is 0. So if I want to only change in direction, I'll go for the magnetic field. If I want both the change in direction, both the change in kinetic energy and direction, I'll prefer the electric field. Very difficult in electrostatic field to control all. So the magnetic field is what widely preferred. So last one more case we'll discuss. Third one, x equal to root 3 r by 2. Root 3 is 1.7. So if I substitute here, sine theta is equal to x by r. So theta equal to how much deviation will be? 60 degrees it will come. Then again the times, what is the deflection? mv by qb 1 minus cos theta. Look at the deflection now. Definitely is a different. What about the time spent? T is equal to omega theta by t. So this will become pi by 3 by omega, or bq by m. Pi m by 3 bq. This is a time spent. The same diagram. If you want, I'll bring the same diagram. Nothing. Here I'll write x equal to r by root 2. So the deviations will be different. Now this will become x equal to root 3 r by 2. Okay, so we can, by varying the width, we can control the deviation and the deflection. Let me put x equal to r. What conditions will come? The last one, x equal to r. I think then we'll make x greater than r. Then we'll see x equal to r. I think this will be the fourth case. The field in fact will be like this. There you'll get confused. That's why I didn't bring it. So now this is x equal to r. You can see clearly from the charge particle, how much it will deviate. We know sine theta equal to x by r, r by r. Theta equal to pi by 2. The deviation will be 90 degrees. So the charge particle will just graze. Afterwards, what will happen? It's not going to. It's going to. I think I should. I to remove this green color part. I'll bring the diagram, because if I should not keep that pink color one. It should be removed completely. Only part. Okay, yeah, fine. So this will be our The charge particle afterwards, it will just graze. It will not enter into magnetic field further. So this will be the motion of okay, I think I gave best diagram. So what is the deviation? You check it, pi by 2. Now why it happened? Because the B bar is into the plane, and look at that, x equal to r. So what is the deviation? 90 degrees. So now I think what is the final conclusion? Here, if you want, you bring that dotted line to show that it's a part of a circle. There's a method. Everywhere I had to change the particle again. This is the wrong perception. The particle will not move afterwards. What if the particle? Particle is going to move in a circular path. It's going to move in a straight line path. I'll take it out. Somebody asked even this also doubt. Okay, fine. But I should put a dotted line. This should have been part of a circle. If the magnetic field were present everywhere, it would have been a circle. Hope now you're able to understand this. Here only I'll make small changes. Yeah. Somebody are thinking that after leaving magnetic field region, it will move in that pink color. Pink color is a path. Afterwards, why it will move? It will move in a straight line path. Hope this dotted line will further show that path of the charged particle outside the magnetic field. Everything I'm putting in systematic order. Please do understand. There's nothing big, and it's going to continue here. Okay, there's a deviation for x equal to r. We do get a deviation of 90 degrees. What is the time spent? Again, the time spent is given by omega equal to theta by t, pq by m, pi by 2 t. X greater than r. We'll see. I think that this will be the last thing, which is very, very important. Here only, let me go for it. X greater than r. Just I'll make x greater than r. We'll see what conditions will arise. Fifth one. X greater than r. You can pick up any value. It doesn't matter. So I'll write, let it be x equal to 1.2 r or 1.5 r. Just greater than r is enough. The charge particle will come here. Will deviate by 180 degrees. This will be center of circular path. I made x equal to 1.5 r. Doesn't looks okay. No, still not there. See now. Okay, at least 1.5 r it appears. This is what r, no? At t equals 0, the particle is here. After some time t, it is available here. What is the different deviation? 180 degrees. Time spent is equal to theta by omega, pi by bq by m, pi m by bq. There's a time spent by the charged particle inside the magnetic field. And what about the radius? The radius again depends upon the same, with what speed it enters here. Okay, I think this is the best thing available for us to control the motion of charged particle. What you can bring the magnetic field by varying the width of the field, we can control the deviation. There's a primary aspect of our discussion. By varying the width of the field, we are going to control the path of a charge particle. How you want to make the charge particle to move, you can make it. Okay, let's see next situation we'll analyze. If there is a